Right. So, welcome to UV Physics Academy, and this is the bridge course of mathematics for CSIR net coaching. The summary of the last lecture we have discussed is differentiations, that means derivatives. Now we are going to take applications of derivatives. Applications of derivatives. This is a very important, so listen carefully. So here we are going to discuss a few applications. First let me take the first one. For example, they have given one function is given to you, and we want to check whether that given function is a differentiable or not at a particular point. So we are going to check the given function is a differentiable or not. Function is a differentiable or not. What is the problem? Why all the functions cannot be differentiable? Sometimes, for example, you have a continuous function. So whenever a function is continuous, we cannot say the function is a differentiable. A continuous function may or may not be differentiable. First of all, how to check this function is a differentiable or not? Okay, so let us suppose they have given some function f of x. Okay, so I am taking some graph like this, the graph corresponding to f of x. Okay, some graph is given already. Let us suppose here we have a point, let us say x is equal to a. Now we would like to check, just like any curve or something like that you can take, right? Now I would like to check at this x is equal to a whether the function is a differentiable or not. So what to do? Whenever you are going to check the differentiability at a particular point x is equal to a, what we have to do is we have to find the derivative of f as x is approaching to a from left side, as well as you have to find the derivative of f of x as x is approaching towards a from right side. Generally, whenever it is approaching to from right side, we will take it as x tends to a plus, and whenever it is approaching to left, approaching from left side, then we will take it as x tends to a minus. So we have to find the derivatives of the given function as x tends to a plus as well as x tends to a minus. That means from left side to a and from right side to a, just like limits we find. And if both the derivatives are same, then the function is said to be differentiable, otherwise no. So that means you find the derivative of f with respect to x as x tends to a minus. That means x is approaching to a from left side, and this is the derivative df by dx whenever x is approaching to x tends to a plus, that is x is approaching to a from right side. If these two integrals are same, then we will say this function f is said to be differentiable. Okay, so let us take a small example. Now here I am taking y is equal to mod x. Mod x is a continuous function, no doubt about it. So if you draw this function, let us say this is the x-axis and this is the y. Okay, so they have given y is equal to mod x. First, if you draw the mod x curve, it will be like this. That means for negative values of x also you will get the positive value only. That's why it is an even function. First of all, mod x is an even function. That's good. Now see, this mod x is a continuous function, no doubt, and here we have origin. Now I am going to check whether this mod x is the differentiable or not at x equal to a. So for that, First let me take the definition of mod x. So the definition of mod x is given by, this is a very crucial, please remember, again it will come in our coaching. Here you have to take a plus x. While you are doing the problems involving the Dirac delta function, so this property is very important, so please remember. Mod x is equal to plus x for x greater than 0 and minus x for x less than 0. Now you have a doubt. At x equal to 0, what is the mod x1? What is mod x? Where I have to include? Whether I have to include x less than or equal to 0 or x greater than or equal to 0. Remember, mod x definition, x greater than or equal to 0. I repeat, x greater than or equal to 0. That is plus x. So you should not include this equality for both. So minus x is defined only for x less than 0. As per the definition, this is x greater than or equal to 0, it takes plus x. Please remember that, that's very crucial. Okay, fine. Now as per this checking condition, now I am going to find df by dx or dy by dx, whatever it may be. Okay, so you can take dy by dx. I am finding a dy by dx as x tends to 0 minus. 0 minus means what? It's a left side of a. So the left side of a, that is x less than 0. This is x less than 0 and this is x greater than 0. So your function is already defined, please check. Mod x is equal to plus x for x greater than or equal to 0. Mod x equal to minus x for x less than 0. So that's why this is simply dy dx of your y value on the left side, that is a minus x. So this is a minus 1. And now I am going to find the right side value, that is a dy by dx as x tends to 0 plus. That is the right side. So that side means x greater than or equal to 0. Here it is a plus x. dy by dx of x. Okay. So this differentiation is a plus 1. So but unfortunately both the derivatives are not same. That's why we can say dy by dx as x tends to 0 minus is not equal to dy by dx as x tends to 0 plus. So you are checking the differentiability at x equal to 0, but unfortunately whenever your function is approaching towards 0 from the left side, the derivative is minus 1, and whenever it is approaching to x equal to 0 from the right side, the derivative is plus 1. So both are not same. That's why this mod x is not differentiable at x equal to 0. So mod x is not differentiable at x equal to 0. So if anybody asks the mod x is a differentiable or not, you have to say the mod x function is a differentiable in this region, that is a minus infinity to 0. So 0 is not included. If I give this bracket, that 0 is not included. If I have given the square bracket, I hope you know that variation to 0 to infinity. Minus infinity to 0, but 0 to infinity, but 0 is excluded. Of course, infinity is also excluded. Okay, so mod x is a differentiable only in this range, in the range. So although it is a continuous, but it is not a differentiable at x equal to 0. So your conclusion, you can say like this. So a continuous function may or may not be differentiable, may or may not be differentiable, because the mod x is a continuous function, no doubt, differentiable It's a continuous function, but it is not differentiable at x equal to 0. Come on, take it. Right, ready. So go to the next question. Here they have given this function, some graph is given, and they are asking whether it is a differentiable at x equal to 0 or not. Now carefully observe. So here this is the straight line passing through origin, that's why we can take it as y equal to x, and it's a parabola, so that's why we can take y is equal to x square. So the left side of 0 we have the function y equal to x square, and the right side we have function y is equal to x, but they have given a graph and they are asking that function will be differentiable or not at x equal to 0, but it is a continuous, no doubt it's a continuous. Continuous, how you will check? By using limits. Just find the left side limit and the right side limit. If both are same, then we can say that a function is a continuous. Okay, so now I am finding dy by dx as x tends to 0 minus. 0 minus means it's a left side derivative. The left side derivative, I hope you know, this is a 2x. Okay. And here x tends to 0, that's why if you take the limit 2x and x tends to 0 minus, so how much it is 0. Okay, so next one, if I take dy by dx as x tends to 0 plus, this is the right side, and if you take the right side function derivative, that is a 1. So as a limit, if you take the limit, of course it is a 1 as x tends to 0 plus, and this value is a 1 only. Okay, so if you see this one, these two derivatives are not same. That means dy by dx as x tends to 0 minus is not equal to dy by dx as x tends to 0 plus. So what is the conclusion? The given graph or the given function, the given function is not differentiable, so at x is equal to 0. Now let us take one more. Okay, and the third one they have defined. Third one something like this. So here this is the x-axis and this is the y-axis. They have given the function like this, something like this, and the point is given as x equal to 1. Here x equal to 1 they have given this point, and this value they have given it as 2, and the graph is given. And they are asking the corresponding function is a differentiable or not at x equal to 1. They are asking to check at x equal to 1. So whenever you are checking the differentiability, first you have to write the function on the left side as well as right side. So now the left side is very clear. So your y is a constant. That's why here y is equal to 2. So the right side function, sorry, left side function. And what about the right side? If you see carefully, this is also a straight line. So pass, of course, this is not very properly drawn. Okay, it's okay. It's a straight line, just like y is equal to mx or something like that. But unfortunately, at x equal to 1, the y value is 2. So that's why I can take y is equal to 2x. Then just cross check. Put x is equal to 1 here. Are you getting 2? Yes. That's why you can take y is equal to 2x here. Now as usual, I am finding a dy by dx as x approaches to 0 from left side. So that is the left side function derivative, it's a 0. And similarly, I am going to find dy by dx as x approaches to 0. We are not finding at x equal to 0. We are finding at x equal to 1. That's why this is a 1 minus. That is the left side of this one. This is x tends to 1 minus. and this is x tends to 1 minus, and here we can take x tends to 1 plus. Okay, so wait a minute. So 1 minus, of course, it's a constant derivative is a 0. And here dy by dx as x tends to 1 plus, that is the right side of x equal to 1. You are having the function y equal to 2x and its derivative is 2. Unfortunately, both are not same. That's why we can say not differentiable at x equal to 1. Next one, you please try. Come on. So take these things. Just pause the video and try to do it yourself, and after that check the answer, please. So I hope you have completed this, and let us go to the next one. So you please pause the video and try to do it yourself, and after that check your answers. Now they have given the graph like this, and they are asking the differentiability at x equal to 1. So here I am taking dy by dx, the derivative of the function dy by dx as x approaches to 1 from left side, that is x tends to 1 minus. So we have to take this function, that is nothing but dy dx of root x, which is 1 by 2 root x. And if you take the limit, that is x tends to 1, so this will be nothing but limit x tends to 1 plus is nothing but 1 by 2. Next I am taking the right side derivative dy by dx as x tends to 1 plus. So here this is my function, that's why dy by dx of the function is a 2x minus 1, so which is nothing but a 2. So the left side and the right side both are different, that's why this is not differentiable. At x is equal to 1. So the next one, try yourself. Again he is asking at x equal to 1 only. This is the point, okay. So left side function is y equal to x, right side function is y equal to 2 minus x. So come on, do it. Dy by dx as x tends to 1 minus, that is from left side it is approaching to 1. What is your function? X. So what is its derivative? 1. Next I am taking dy by dx when x approaches to 1 from the right side plus. So your function is y minus 2x. What is its derivative? Minus 1. And both are not same. So both are not equal. If both are not equal, then the function y is not differentiable at x equal to 1. I hope you understand this. Come on, check it. Please check your answer. Don't simply copy. First pause the video and try to do it yourself, and after that check whether the answer is right or wrong. Right. So we have completed this first application, that is to check whether the given function is differentiable or not at a particular point. Now this is the second application. The second application is very important. This is the stationary points. Stationary points, or in physics we used to call these points as equilibrium points. Equilibrium points. This is a very important. Listen please. So first, what is meant by stationary point? Stationary, not changing something. Oh, so at that point the function value is not changing, and neither it's not increasing or it's not decreasing, something like that. At that point the function value remains constant or remains the same. If a function value remains constant or remains the same, at that point if you find the derivative, what you will get? You will get 0. Okay, so wait a minute. Now here let us suppose y is some function f of x. Okay, so now I am finding the derivative of that. So the derivative we have already discussed, the rate of change of the function. The derivative is nothing but simply I can take df by dx. So the derivative is also called as a gradient of the function f of x, and geometrically we can use one more word, that is a slope of f of x, something like this. Okay, now for example I am taking a df by dx is equal to 0. Then I got some x values, x is equal to, let us say, a comma b comma c, so on. And these points are called stationary points. These points are called stationary points. So I hope now you understand what is meant by stationary point. A point at which its a slope becomes 0. That means whenever a curve is given and if you take the tangent, and the tangent will be just like a horizontal tangent. So horizontal tangent slope is what? 0. Okay. So stationary point, that means if you see the definition, a point at which the slope of the function is 0. What is the meaning of slope is 0? Whenever you said slope is 0, that implies it's a simply horizontal tangent. It contains some horizontal tangent. Because the horizontal axis, x-axis slope is 0, but y-axis slope is infinite. Okay, so anyhow, that's it. This is graphically derivative is nothing but the slope, and if slope is equal to 0 at a particular point, and that point is called stationary point. And how many types of stationary points are there? Now here we have types of stationary points. So we have 3 types of stationary points. Okay, so one is a minimum, and another is a maximum, another is a point of inflection. This concept is very important, pay attention. It's a point of inflection. So what is meant by minimum? And at that point the function value is minimum. If you want to say function value is minimum at a particular point, on either side of that point the function value should be increases. Okay, so for example, if you have a situation like this, if you see carefully, let us say a particular point here, A here, let us say this is A. Okay, now so at this point I have some horizontal slope, or a slope of the curve at x equal to A, slope is 0. Let us suppose slope is 0. Now if you see carefully, with respect to A, this side function value is increases and this side function value is increases. So on either side the function value is increasing, means we can say at x equal to A the function value is minimum. So that's it. Here I am taking x equal to A as a minimum. Next, still not understanding. Now for example here we have some function variation, something like this. Now I have taken a point B, let us suppose, and here also the slope at that point is 0. And if you see with respect to B, either side, this side function is decreasing and this side also function value is decreasing. So definitely at this point x equal to b, the function should have maximum value. So here either side of b, f of x is decreasing. F of x is decreasing. That's why the function is having a maximum value at x equal to b. And here either sides of a, okay, f of x is increasing. F of x is increasing. That's why at x equal to a, the function is having minimum value. And if I take another example, something like this. Now see, just like this. Okay, so let us suppose here some flat, of course it's not properly, okay, it's okay. It's not an issue. Okay. Now let us suppose there exists a point C where the slope of the function become a 0. Now if you see carefully, on the left side of this point C, on one side the function value is increasing and another side the function value is decreasing. Okay, so one side it is increasing, another side it is decreasing. So we can't say this is a neither maximum nor minimum. So such type of point we call it as a point of inflection. So these are the three types of stationary points. One is a minimum. So on either side of that point the function value is decreasing, that is called a minimum. At that point function is having minimum. The function value, either side the function value is increasing, so that's why the point is called minimum. And if you have a particular point, some point B, okay, either side of this point the function value is decreasing, so we can say that is a maximum. And one side increasing, another side decreasing, that point we can say the point of inflection. Come on, please take it. Ready. So now let us take one function, it's an arbitrary function which is varying with respect to x. And here we have the derivative of that function, first derivative df by dx is equal to 0, and I got some x values, let us say a comma b comma c, and these points are called stationary points, right? So let us discuss more clearly what are the properties of these stationary points. And earlier we have discussed the three types exist. One is a minimum, another is a maximum, another is a point of inflection. Now if you see here with respect to a, and this side function value is increasing, as well as this side also function value is increasing, that's why it is called minimum. So there will be only one minimum for the given function, or many minima will be there. Yeah, many minima will be there. So those are called local minimum. And overall one value at a particular point the value is a minimum, that is called principal minima, something like that. But it's okay, let us suppose here I have taken only one minimum. And if you see with respect to b, here the function value decreases on both sides, that's why this point is nothing but maximum. Unfortunately here one side increasing, another side it is decreasing, that's why this is a point of inflection. This is a point of inflection. Now let us see what are the properties one by one. First I am taking this point A. So I would like to discuss this point A first. 1 minute. So point A we call it as a minimum. We can say local minimum also, it's no issue, right? Minimum. Once again, please take that part. So this is the curve, okay? So here we have at x equal to a point we have. Now I request you please take tangents on either side of this curve, point A. on either side of this point A, just take a tangents. Yeah, I have taken tangents. And after that, please find the slopes. If you want to find the slopes, you have to take a horizontal line because the angle made with the positive x-axis we have to take. So I hope you understand. This is the angle made with the positive x-axis and this is the angle made with the positive x-axis. Now carefully observe. And I can take this as the initial theta because the function starts from here. That's why I am taking initial theta here. And this is the final theta. And if you see carefully, your initial theta is greater than 90 degrees and this theta is less than 90 degrees. So what? So I hope you remember the slope m is equal to tan theta. Okay. So if theta is acute, that means less than 90 degrees, the m is a positive slope. And theta is obtuse, that is greater than 90 degrees and the slope is negative values. Because theta less than 90 first quadrant tan is positive and theta greater than 90 second quadrant tan is negative. That's good. So can you please tell me how the slope is varying with respect to A? So here we are talking about point A. So with respect to A, the slope value is changing from a negative value to positive value. Here the slope is negative and here the slope is positive. So with respect to A, how the slope is changing? The slope is changing from a negative value to positive value. So that's why the slope is changing from negative to positive value. If it is changing from negative to positive value, can you please tell me, is it increasing or decreasing? Definitely increasing. So that's why with respect to A, the slope that means df by dx, is it increasing or decreasing? Increasing. For example, let us suppose with respect to time, the length is increasing. With respect to time, the length is increasing. Just like our height from the childhood to 25 years or 24 years, 28 years, like that. So our height is increasing. It's a definitely increasing function. So I mean in between 10th class to intermediate, in that duration of the time, if you differentiate the height with respect to time, what you will get? Definitely you will get a positive value. Why? The function is increasing with respect to time. For example, if you take a piece of chalk and you are writing and you started the class at 9 o'clock and you are writing, the length of the piece of chalk is decreasing. So if you find the derivative, what you will get? Definitely you should get a negative value with respect to time because it's a decreasing function and here it is an increasing function. So I hope you understand. The slope is increasing. Okay, here slope is increasing, that is the df by dx value is increasing. If I find one more derivative, that is d by dx of df by dx. Just imagine this is your height in the childhood. So the height function is increasing. Again, if you differentiate it, definitely you will get a positive value. Because with respect to time, the function is increasing. That's why definitely you will get a positive value. One more time if you differentiate. I hope you understand this point. So we can say like this, a second derivative positive, that means a d square f by dx square is greater than 0, that is positive. So this is the condition for which point? A. That A is what? Minimum. So at minimum, the second derivative of the function is positive. Okay, come on. So the next one, we can discuss this B. Just wait. Okay, so I hope just pause the video and do it yourself or copy. Now see, next let us go to this B. Okay, so here I am taking this point B, here I am taking point B. So let me take the curve first. So this is the curve with respect to B. So I am taking the tangent here. One more time, I am taking the tangent here, and this also I am taking tangent. Now I would like to study how the slope is varying with respect to B. I have taken a horizontal line, that is a positive x-axis, x-axis. So here I hope you understand, this is varying like this, means this is the initial theta and this is the, we can say, final theta. This is a greater than 90 degrees and here it is a less than 90 degrees. So initially your slope is a positive, this side of B, and this side of B your slope become a negative. Slope become negative. So with respect to B, how the slope is changing? It is changing from a positive value to negative value. So finally we can say, with respect to B, slope is decreasing. If the slope is decreasing, that means it is coming from positive value to negative value. So that's why df by dx is decreasing with respect to B. So the same example earlier I have given a piece of chalk example. The length is decreasing with respect to time. So one more time if you differentiate, definitely you will get a negative value because it is decreasing. So one more time I am differentiating. One more time I am differentiating. That is df by dx again, d by dx of df by dx. So what you will get here? Negative. So we can say the second derivative is negative at B. So finally d square f by dx square is a negative. Negative means less than 0. So negative, where at x is a maximum. If the function is having a maximum at a particular point, at that point the second derivative is negative. So final conclusion, at minimum we got the second derivative d square f by dx square. At x equal to a we got a positive value, and at maxima, that is a d square f by dx square at x equal to b, this is a negative maximum. So now we can write this, because here it is neither maxima nor minima. So this point C, so this is neither maximum nor minimum. If it is a minimum, second derivative positive. If it is a maximum, second derivative negative. But neither maximum nor negative, that means neither positive nor negative, then what's the value? 0. So that's why d square f by dx square equal to 0. So this is the condition for point of inflection, and this will be the condition for maxima, and this will be the condition for minima. So minima, second derivative positive, maxima at that point second derivative is negative, point of inflection at that point second derivative is 0. But for all these 3 points, your slope of the function at that point, it should be a 0, because all these 3 points are called stationary points. Got it? Come on. Ready. So let us take one problem here. So they are asking to discuss the nature of stationary points of the following functions. And here they have given a polynomial. So this polynomial order is 3. If the polynomial order is 3, so how many stationary points are possible? Simple logic. How many stationary points are possible? Polynomial order is 3. Once you differentiate it, that order become 2. because x cube differentiation become x square. Then it become a cubic equation become quadratic equation after derivative. And you are taking the derivative and equating to 0. A quadratic equation you have, that is ax square plus bx plus c equal to 0. Then how many roots you will get? 2 roots, minus b plus or minus root of b square minus 4ac by 2a. Okay, so if nth order polynomial is there, its a derivative will be n minus 1. So n minus 1 stationary points are possible. Maxima, minima, point of inflection, that is a different story. So here that is what we are going to discuss, the nature of stationary points. Now let us start. Here the given function f of x equal to 2x cube minus 3x square minus 36x plus 2. So as usual, first you have to take the derivative of the function df by dx equal to 0. Now just a differentiation, that is a 6x square minus a 6x minus 36 equal to 0. And here you can simplify, that is x square minus x minus 6 equal to 0. So if you find the roots, this will be x square minus 3x plus 2x, okay, and minus 6 equal to 0. And this is x minus 3, x common, plus 2 common here, x minus 3 equal to 0. So here you will get x equal to 3 comma x equal to minus 2. So a cubic equation contains 2 stationary points, x equal to minus 2 and x equal to 3. Now we want to check these points are either maxima or minima or point of inflection. For that, what we have to find is second derivative. Remember, whenever you are finding the second derivative, we should not consider the simplified first derivative. Here we have to take the first derivative. So this is the simplified value of the first derivative. Okay, we should not consider that. We have to consider the original one. The original one means this one. But don't take 0. Here you are not equating to 0. Just you are finding the second derivative. That means one more time derivative of the first derivative. So your first derivative is a 6x square. This one, original we have to take. We should not take the simplified one. Because the right hand side is 0. That's why we simplified. But here nothing is a 0. Again one more time derivative. 6 2s are 12x minus a 6. Now you have 2 points. Let us substitute these 2 points. Now I am taking x is equal to minus 2. Take it and substitute. So your second derivative here, d square f by dx square is minus 30. If it is a negative, is it a maximum or minimum? Maximum. So this is a maximum. Okay. So the function is having a maximum value at x equal to minus 2. And the next one, if you take x is equal to 3 here, and again substitute in the second derivative, that is a d square f by dx square equal to again 30, because this time it is a plus 30, 36 minus 6, 30. So is it positive or negative? Positive. This is positive, and here it is a negative. Since it is a positive, second derivative positive, that's why it is a minima or maxima? Minimum condition. That's it. So your function is having minimum value at x equal to 3. Remember always, either maximum or minimum, we will use a common word called extremum. Extremum. If I use the word extremum, so that is the function is having either maximum value or minimum value, something like that. Okay. So can you please try the second one? Just pause the video and try to do it yourself. Otherwise, please check. Ready? First do it yourself, be confident, and just pause the video and do it and check the answers. Then you will get confidence. And next come to this. And here we have the function as usual. The first derivative we have to take equal to 0. So that is a 3x square, because the stationary point's condition is the first derivative 0, minus a 6x plus 3 equal to 0. Just now I told you, if right hand side is 0, you can simplify, and this will be x square minus 2x plus 1 equal to 0. If you observe carefully, this is a minus b whole square, that is x minus 1 whole square. So here we got x equal to 1 and x equal to 1. Oh, surprising. Here we got double roots, repeated roots, not double, repeated roots. Repeated roots. So what is the significance of this? Let us see. Next I would like to check what is this. That's why I am taking a second derivative again. So I told you, you should not take the simplified one. You have to take the original one, this one, and take the second order derivative, that is a 6x minus a 6. Now you have the two roots that are both are same. That's why I am taking x equal to 1. If you take it and substitute, that implies I am getting a d square f by a dx square equal to 0. Okay. This is the condition for neither maxima nor minima. It is a point of inflection. So x equal to 1 is a point of inflection. So finally we can conclude that if any polynomial is having a repeated roots, that is once you find the first derivative and equate to 0, you got x equal to 2 comma 2 comma some other roots will be there. But if any repeated roots are there, and that will be the point of inflection. This is one of the case. Repeated roots, definitely it will be point of inflection. Come on, take it. So I hope you have completed. So the next one, a potential energy is given. V of x is equal to 1 by 4 x square minus 2 whole square. So actually this was the previous gate question, and they are asking what is the nature of the stationary points. Let us proceed the same process. So here I am taking the first derivative dv by dx equal to 0. Now 1 by 4 as it is, because it's a constant, and it is in the numerator, that's why here 2, and we are assuming this as a something square differentiation, 2 into something square differentiation, 2 into something, into again whatever you have assumed something, you have to differentiate it again. That is a chain rule. Don't write the chain rules like that. So please try to practice like this only. 2 something x square minus 2, again differentiation of the something. This is your assumption. Its a differentiation is a 2x. So finally we can cancel this, of course. It is equal to 0. And this 2 and 4 gets cancelled. So finally x into x square minus 2 equal to 0. Obviously this is the polynomial of order 4. X square is there and a whole square is there 4. That's why there will be 3 stationary points. And out of this, of course, what are those stationary points? X equal to 0. And here x square minus 2 equal to 0, which implies x equal to plus or minus root 2. I hope you know this. Now finally I got x equal to 0 comma, x equal to root 2 comma, x equal to minus root 2. Let me check which is a minimum, which is a maximum. For that I have to find the second derivative, d square v by dx square. So of course here it can be cancelled because this only numerator denominator gets cancelled. So you please take this function. That is your original function. After cancellation you can do, no issue. So don't take it as a uv, please differentiate it. So that's why d by dx of, what is a dv by dx? Just multiply x cube minus 2x. I hope you understand. This is my first derivative I have taken here, and one more time differentiation. So how much? 3x square minus 2. Now I'm going to substitute one by one. First x equal to 0, take it and substitute. I got minus 2. That means the second derivative d square v by dx square is minus 2. And the next I have taken x equal to plus root 2. And if you take it and substitute, that will be, so second derivative d square v by dx square, so equal to here, so 4. And similarly x equal to minus root 2, if you take it and substitute, the second derivative d square v by dx square equal to, so here also it is 4. So here this is a positive and this is also positive, so we can say these two are minimum. Okay, and here it is a negative, that's why this is a maximum. So function is having three extremum values. Three extremum. Extremum means either minima or maxima, and two are minima and one is a maxima. That's it. Come on. Right. Let us practice some problems based on this maxima and minima. So here they are asking, find the maximum value of x square plus 250 by x is. Remember, whenever the question is like this, find the maximum value or find the minimum value, something like that, then no need to check whether it is minima or maxima. He is already asking that value only. So my advice, don't waste your time to check whether it is really having maxima or minima. He is asking that question only. So what is the maximum value or what is the minimum value? Then no need to check. My advice, just find the first derivative, equate to 0 and get the x value and take it and substitute. That's it. Okay, now ready. So this is my given function. Here they have given f of x is equal to, so f of x equal to, this is x square plus 250 by x. Now let me find the first derivative. This is a df by dx equal to 0. So it is the numerator, that's why 2 as it is, of course plus 2. Okay, if it is in the numerator plus 2, if it is in the denominator minus. So to decrease the power, that is x. But here it is in the denominator, that's why minus, here power is 1, 250 by increase the power, that is x square. So equal to 0. So if you cross multiply, so this will be, if you bring this side and multiply, 2x cube equal to 250 and x cube equal to 125 and x equal to 25. Now no need to check whether it is having a minima or maxima. What I am saying is, just take the function again, f of x equal to x square plus 250 by x. Now please substitute f of x at x equal to 25. Just substitute 25 square plus 250 by 25. So this is oh, I'm sorry, this is not 25, 5. So this is the x cube 125. It's not 625, sorry, it's a 125. That's why it is a 5. So just substitute x is equal to 5. So then you will get 5 square plus 250 by 5. So this is a 25 plus 50. The answer is 75. Here it is 125. X cube is 125 means x is equal to 5. That's it. Okay. That's it. And let us go to the next one. So here f of x equal to x power 1 by x has a maximum at x equal to. He is not asking the maximum value. At what value of x the function is having maximum. This is he asking. Okay. So no problem. The given function f of x equal to x power 1 by x. Earlier I told you, whenever exponent is a variable, if you want to differentiate it, you have to apply logarithmic differentiation. Apply logarithm on both sides. Log f equal to 1 by x into log x. Now go for implicit differentiation, that is a 1 by f df. This is the implicit differentiation. This is a u and this is a v. Minus 1 by x square dx of course log x is as it is, plus 1 by x as it is, log x differentiation 1 by x dx. So dx you can bring this side, that means dy by dx. Okay, so here I have 1 by f, of course let it be there only, and here I got minus 1 by x square log x plus 1 by x square, because the dx I brought this side. Now we know the first derivative is equal to 0, that's why we can write minus 1 by x square log x plus 1 by x square equal to 0. Okay, so you can bring this term that side, and finally I will get log x equal to 1. So x is equal to e raised to 1. So at x equal to e, the function is having maximum value. If they are asking what is that maximum value, then you have to take the function again x power 1 by x, and you have to substitute, that is x equal to whatever you got e, that is e power 1 by e, something like this. Okay, next problem. So the maximum value of the, here they are asking maximum value of the function 1 by x whole power x. Try to do it yourself, and after that please check. Now here my function f is equal to 1 by x whole power x. As usual, the exponent is having a variable. Apply logarithm, log f equal to this is nothing but x log of 1 by x. Okay, so you better to bring it to the numerator, that's why we can say this is a minus x log x. Log 1 by x is nothing but minus log x, and this is log f. Now do the implicit differentiation, that is a 1 by f df equal to, here uv formula, minus of x as it is, and this is a 1 by x dx, and plus log x as it is, and the differentiation of x is 1, that is a dx. Now you just take out common, so this is nothing but a minus of 1 plus log x, and here you can bring this dx this side, df by dx, and you can keep this 1 by f as it is, no issue, because the first derivative is equal to 0, that implies 1 plus log x equal to 0, and log x equal to minus 1, x is equal to e raised to minus 1. At x equal to e raised to minus 1, the function is having extremum value, or of course he has given maximum, and take it and substitute. He is asking the value. So whenever you want to find the value, just take this point and substitute. So that is e raised to minus 1. So 1 by e raised to minus 1 whole power e raised to minus 1. I think this can be written as e power 1 by e. Okay, so the next problem, please take yourself, please do it yourself, and after that check the answer. Okay, so here they have given a function again, f equal to 1 by x whole power 2x square. So this is also the same thing, similar one. Apply logarithm on both sides, and this is I request you do it yourself, 2x square log x, and proceed implicit differentiation. So that is 1 by f df. So please proceed with the implicit differentiation, that is 2 of course common, and 2x dx, of course log x is as usual, plus this time x square as usual, 1 by x into dx. So dx you can bring this side, and finally here I am getting a 2, and this is a 2x log x plus 1, sorry, this is x. So you can bring this df this side, that is a dy by dx, and here 1 by f. So this first derivative is equal to 0. So we can say 2x log x plus x equal to 0. I request you do it yourself, don't copy, and bring that side. Finally log x equal to minus 1 by 2, and x equal to e raised to minus 1 by 2. and please try to do it yourself. Oh, he's asking the value. Now then take the function f of x, again 1 by x raised to 2x square, and f of x at x equal to e raised to minus 1 by 2. So please take this and substitute 1 by e raised to minus 1 by 2 whole square, of course whole power 2, and here again x square, that is e raised to minus 1, because x square and x is e raised to minus 1 by 2. I think this can be written as, you can write it as e power 1 by 2, and again whole square is there. That's why it is e raised to e power minus 1, or we can say e raised to 1 by e. Right. So continue the next problem. So here they are asking what is the maximum value of the function psi of x equal to x e raised to minus alpha x. So as usual, take the wave function psi of x equal to x e raised to minus alpha x. So take the first derivative, that is d psi by dx. Okay. So here you have to apply UV formula. So first function as it is, and the second function differentiation e raised to minus alpha x minus alpha. You just pause the video and do it yourself, and after that check. Plus x differentiation is 1 and the second function as it is and equate to 0. Now here it is e raised to minus alpha x common. So minus alpha x plus 1 equal to 0. So either this will be 0 or this term will be 0. But here this will be 0 only at infinity, so that's why no need to consider. And here alpha x minus 1 equal to 0, so x is equal to 1 by alpha. So at that point the function is having maximum value, and if you want to find the maximum value of the function, just take this x value and substitute, that is 1 by alpha e raised to minus alpha into 1 by alpha, alpha gets cancelled, 1 by alpha e raised to minus 1. So this is the maximum value of the function. Okay. So next. So I hope this is completed, and go to the next question. So here some problem is given. A political party orders an arch for the entrance to the ground in which an annual convention is being held. The profile of the arch is of having this equation, following this equation, and they are asking what is the maximum possible height. So here the height equation given, so that's why first to take that equation, that is y equal to 2x minus 0.1 x square. So you have to maximize this, we have to maximize this function, that's why find the first derivative dy by dx equal to 0 and get the x value and keep it aside. Okay, and he's asking maximum possible value, whatever the x value you got, just take the function again, that is 2x minus 0.1 x square, and substitute whatever the value you got and try to do it yourself, and then the maximum value, the answer will be around 10 meters. I think you will get a 10 meters exactly. So please check whether you got this answer or not. Do it yourself. And next one, consider the projectile motion of a particle of mass m with equation. Here they have given projectile motion. So I hope you remember from the intermediate. So this is the projectile motion x and y, and here the body is projected like this with the initial velocity u, something like this, at an angle theta. Now projectile motion equation is given, y is equal to u sine theta into t minus half a gt square. Now is asking maximum height. So first here the variable is a theta, not theta, t, because at a particular angle you are projecting. So with respect to time its position is changing. So here the variable is t. So that's why first differentiate dy by dt equal to 0. You are differentiating with respect to time. So that's why u sine theta minus this is a gt, 2 gets cancelled. So this should be equal to 0. That's why t is equal to u sine theta by g. You know this. This is the time taken to reach the maximum height, time of ascent. We can say something like the time of ascent something. Okay, and take this time and substitute, then you will get maximum height. Because the time taken to reach the maximum height is nothing but u sine theta by g, and take it and substitute. This is a u sine theta into again u sine theta by g, and here minus half, this is a g t square, that is u square sine square theta by g. G gets cancelled, and here one second, yeah, g square, sorry. So g square and sorry, this is g, and here it is a square cancel. So finally u square sine square theta by g, and here it is u square sine square theta by 2g. Finally you will get this one. I hope you know this. The maximum height in the projectile, you will get u square sine square theta by 2g. Okay, yes, come on. So this is about applications of differentiations, first part, and we'll meet again in the second part. So please practice properly. These are very important for our main course. Okay, thank you, and we'll meet again.